Hi, welcome back. Today we want to talk a bit more about cryptography. In particular, we'll focus on explaining what RSA crypto system is, including both the encryption scheme and the digital signature scheme. A bit recap. Last time we talked about password security, the importance of sorting, so that just to make it harder for people to recompute, reuse pre-computed hashes to guess your password. We explained in depth how DES work. DES is now a defunct symmetric key encryption scheme. You should use AES, the Advanced Encryption Standard, but understanding how the simplest block cipher works, the importance of cipher block chaining, the different permutations, substitution modes, the S box and P box, and that will just give you a bit more intuition of how to scramble messages, just to make ciphertext look as random as possible. In the meantime, that if you have the key, you can still retrieve the original message. We mentioned the side channel attack, differential analysis. We ended with explaining the DiffieHellman Key Exchange protocol, and it's very important to know that DiffieHellman Key Exchange is a public key crypto system where you can have, you don't have to have pre-shared key. This is an interesting figure that shows that substitution cipher is not very secure because you can still do this statistical analysis on the symbol frequency and then kind of guess. Well, in English, E occurs way more often. T, if you play Wheels of Fortune, you know S, T are the among the most common letters that you can guess correctly. N, M, H as well. So I do recommend you to read a little bit about Alan Turing, how his team cracked the Nazi Germans' Enigma code and the Enigma machine. And Alan built a machine called bomb, which is an electromagnetic device, which is pictured here with a lot of wheels, and be able to, in a very scalable fashion, guess the Enigma encoding, which every day there's a new code. And then eventually they figure out that there is some patterns in how the plain text is structured. So if you know, if you have a good guess that what the plain text is, and then in the meantime you have the ciphertext, and then bam, you're in business, you will have a very high likelihood of guessing the code of the day correctly, and then you can use the code to decode the whole day's worth of communication. And a lot of this deterministic mechanism is the main reason for people to crack this type of symmetric key cipher. Imitation Game, a very well made movie. I'd recommend you to take a look. Questions about class project: should you structure an idea around producing a security solution or protocol and then be able to write the code and evaluate? Yes, this is a preferred option. I highly recommend it. Meaning that if you do this, you'll have a higher grade. Producing a new attack is also fine too. Try something new, and you can justify new by saying there haven't been such solutions. How groundbreaking it should be. I mean, as long as useful, and then no one has done exactly the same thing, then I would consider it new. Would you be okay? Would I be okay if you just do a literature survey, or you just describe an idea? Not as strong. Such projects will not be as strong as creating something new and constructive and do something concrete. And so I do highly recommend you to try very, very hard to get something concrete and be able to implement and evaluate even in a small scale. Of course, you know, this is life. Things may not always work as we want. And so if you tried and it didn't work out, the last two options are fine too. So last time we talked about symmetric key encryption is not very scalable on the internet. You have to share a key. DiffieHellman Key Exchange allow you to strangers to establish shared keys, right? So I want to say a little bit about this. Recall how this is computed, you know, based on the hardness assumption of discrete log. And so I want to explain why it suffers from man in the middle attack. So I'm gonna get my tablet, and then I will stop sharing. All right. So you have a G, right? This is a generator, and we said it has to be a cannot be 0, 1, and so on. And so you have Alice and Bob, and in the normal case, Alice will pick her secret key and then compute the public key, right? And then you have P. Similarly, Bob's secret, you raise G to the power of SB and then mod P. This is Bob's public key, right? So this is public key of Alice. And you send it to Bob, you say, hey, I'm Alice. This is my public key. And then similarly, you know, this is the key of Bob. And you say, oh, I'm Bob. This is my public key. And what Alice does is raise Bob's public key to the power of her secret key, mod P. And this will be the shared key. Okay, this will be the shared key. And similarly, Bob will do raise Alice public key and to the power of SB. And then this is a shared key. And then you verify that they're the same. And they should all equal to G to the power of SA, the power of SB, and then 1P. Okay. So, but this is unfortunately not secure. Why is this not secure? The problem is that when you say, hey, this is my key, I'm Alice, I'm Bob, but then is it really you, right? So you may have man in the middle attacker. So let's just call it hacker. Hacker also can generate a hacker's secret key, and then hacker can raise it to the power, can raise G to the power of SH, And then this is a hacker's public key. Of course, hacker doesn't tell everyone this is hacker's public key. It's just some key that the hacker has a private portion of it, right? So then when Alice says, suppose Alice was fooled into clicking attachment, misled into visiting a website, and then thought that she's communicating with Bob, but actually communicating with a hacker. And so like before, and according to the protocol, Alice will say, hey, I'm Alice, and this is my public key, right? And then instead of relaying this public key to Bob, hacker would say to Bob, hey, I'm Alice, even though it's not Alice, and then give Bob hacker's public key. And Bob, of course, has no idea this is happening, and then will say, this is I'm Bob, and this is my real public key, right? And the hacker, of course, would not give Alice the real public key that Bob has. We'll just give Alice hacker's public key. You see, this is very bad. Right, this is very bad. This step is very bad, and this step is very bad. And of course, everyone is now in the computation mode. What Alice does is faithfully following the protocol and then raise the hacker's public key to the power of SA, just as we defined, and thought that this is a shared key. Okay, key shared. Let's call it 1. And then Bob, this is Bob would do the same thing, except he's also using hacker's public key instead of Alice, raise it to the power of SB. And let's call it K shared 2. And then attacker at this time will have to do 2 things. One is to compute one key for Alice, and the other is compute another key for Bob. And so this is raise it to the power of SH, which attacker knows, right? Because that's attacker's own private key. And we can verify that this is equals to K shared 1. And so they are the same. And this is K shared 2. And this is the same, right? So let's verify. K shared 1 is a hacker's secret key raises to the power of Alice, mod P. And this is G to the SA, right? And then SH, mod P. It is the same. Here it should be also SB, SH, mod P, GS, HSB. It's just a different order, and then they of course they're the same. So you can see that the hacker will be able to communicate with both of them, and then she can relay the actual plain text, or she can modify and tamper with it, but she completely decrypts. The hacker completely can decrypt the communication because she used her own. She used her own secret key, and so this is very bad. And we have some more details here. And but essentially, hacker can can compromise both communication channels. And of course, the key problem came from the first step when you say, oh, this is my public key, but who knows this is your public key, right? You know, who are you? So I'm highlighting step 3 and step 5. This is where the problem is. It's a root cause. Anyone can say I am so and so, but then can you prove? And using the wrong public key is very bad. We have said this as consistently when we talk about certificates and so on. So this is a very concrete example. And you know, this is a very famous back in the 70s, and famous protocol. Later on, people find that it's not very secure. And so go back and take a look and make sure you truly understand why it works in some scenario, but then in some other scenario it fails to prevent man-in-the-middle attacks. So on the internet, of course, we all know that we use RSA, which was invented a year later than DiffieHellman Key Exchange by 3 computer scientists. It's a public key cryptography. It has the encryption and digital signature scheme. And the idea is very similar. So in the sense that you have someone's public key, and you can look it up, you ask the person, or you find it on their website. A lot of people would attach their public key as a signature of their email. And the receiver will be able to decrypt it with a private key and retrieve the message. And RSA, so let's go into the details and talk a little bit about RSA. I want to go back to my tablet. All right. So, so there are 3 steps. One is a key setup. The other is encryption. And then decryption. So if we're lucky, we'll be able to fit everything. The whole thing here. Okay, let me. So you pick. The setup is the most complicated. You pick 2 large primes, not crimes. Okay. And then you compute the product, and then you also you compute the torsion function, which is really p minus 1, q minus 1. Okay, and then n is where the it's called a modulus. A modulus refers to the key length. In some you've seen people say 2048-bit RSA. That refers to the length of n. And then you pick E, and E has to be less than N. Okay. And E, Z are relatively prime to each other. Okay, so they don't share common factors. E and this torsion function. This is Z is the torsion function. And E is the public key. Okay. And this time when you have E, you compute a special D. This D is a private key. Private key is very special, okay? Such that E and D mod N let's see, E and D mod Z. And that is ED product mod Okay, so this is a very special value D is private key. That means E times D minus 1 is exactly divisible by Z, the torsion function. Okay, so there's this special relationship. And then you do, okay, N and E are public key, which you can review. D is a private key. And sometimes people say D and N are private key. And then it's very important you get rid of P and Q, because otherwise with P and Q, you'll be able to figure out the value of D. There are ways to figure out the value of D. And RSA is based on the difficulty of factorization, finding out factors of a number. So it's very important that you don't review P and Q. And then the assumption is, of course, the factorization is difficult, it's hard. And then so that's the setup. The encryption and decryption are exceedingly simple. You have a message you want to encrypt, you raise to the power of E, and then mod the modulus N. And then this will be your ciphertext, right? And then given the ciphertext, the receiver will raise it to the power of the private key D and then modulo N. And this should give you the original message. So this is what RSA is, and we want to know that. So let me just go back here. So here we want to give us some examples. So this is just how you do encryption and decryption, and we're going to show you how how RSA works, so you can get the original message back if you have the right key. But just before that, a little bit of examples, and this is of course very small and will not be secure because you can just brute force and figure out the P and Q. If you know N is 35, right? So, but then just to illustrate, and a lot of times that the public key is short and the private key is long, and D is long, so it's that it's take a longer time to decrypt. Encrypt is faster. So suppose the message is 12. You raise, so it's a base 12 and to the power of 5, and then you do modulo, that give you 17. That's a ciphertext. You get a ciphertext, you raise it to the power of D, which is 29, and this number is a lot bigger, the C to the power of D. But then after modulo C, you get 12 back. So why does it work? So we're gonna show a little bit again. So today we'll just switch back and forth. Hopefully this is, I think, most of the the whiteboard activities. This is the last one. So we want to show it works, and so the goal is to show ciphertext raised to the power of d. This is how you decrypt, right? And then mod n should give you the message back. So we want to make sure that this works. But before we do that, I want to show you that there are two facts that are very important for us. One is that if you know x, if you know p and q are primes, in our case, right, there and n equals p times q, then one of the facts is x raised to the power of y mod n equals x to the power of y mod p minus 1 q minus 1, the torsion function we've seen. Yeah, okay. This is mod. So this is just a fact, and people knew about this for a long time, and just didn't. It's just a number theory fact. But we're gonna use it. Another fact is that you know, when we choose ED, we know ED mod Z. Z is this equals 1. You see, this is just another fact, you know, following our key setups procedure. So let's call it fact 1 and fact 2. So let's just you know to prove this is equal, what you do is you say, okay, what is C? And we know C is the message raised to the power of E. This is how you encrypt, right? So this is C. And so we just rewrite it. Okay, then we can further rewrite. And last time we said that the mod operation, you can always just put the mod to the end. This is just the modulo operations property, basic property. And now we're in business. Look at fact 1. Okay, look at fact 1. This means that we have x times x to the power of y situation, right? And then we have, because n is the product of two large prime, so we can just apply the fact 1 and then say, oh, in this case, because n is a product of two large primes, we can apply this theorem and rewrite it to mod the torsion function p minus 1 and q minus 1 mod n, right? And then we immediately are in good position again, because look at fact 2. Fact 2 said the product of E and D mod the torsion function is equal to 1. So we basically says this is just 1 mod n, and of course this equal to the message. Okay, and you know, when you choose the message, you make sure you chop it in a way that you have a smaller than n messages. So then this shows that it's a correctness. You actually get your message back, and so this is called the correctness of RSA. And I want you to go back home and make sure that you do verify yourself and be able to see indeed you can get your message back if you have the right keys. And we know 2048 bit is the shorted secure key length, and you should also do 4096 bit long keys and to get a stronger security. In the past, RSA has had the RSA factoring challenge, and some of the smaller modulus were broken, and then their cache price. And so use larger keys. So use larger keys always, because especially if you run certain facilities, attackers may use brute force or more of advanced technique that are more efficient than brute force. So that's RSA. That's RSA encryption scheme. We want to later we want to talk about RSA digital signature scheme. However, the version that we told you is not the version that's actually used, because the naive version, what we just described, is has several issues, not just one, several issues. One is that it's deterministic. That means if you have same message, it's always get back to the same ciphertext, right? You raise to the power of E. And then if the M is the same, E is the same, then you get the same C. It's bad because if you have an attacker who is able to intercept traffic, for network communication, we always assume attackers can intercept traffic. Absorbing C prime, C prime, and if all of them are the same, and the attacker can assume that the messages are the same. And so this is very bad. Almost you see a lot of the high profile in the history, the code cracking is based on some aspect of this fact. Another problem of the naive RSA is that the messages may collide. The messages collide into a different message, and in general, this is not good because attacker may also be able to guess certain values and see some correlations between ciphertext and the messages. So for example, if you have, because of properties of exponentiation, if attacker have seen the encryption of M1 and then encryption of M2, and all of a sudden one day you are sending an encryption of M1 times M2, then the attacker will be able to intercept this message and after a whole bunch of trial and error, and then realize this plain text is M1 times M2 because the ciphertext matches. Okay, so in general, we don't want to have any correlation between ciphertext and the plain text. The operation on ciphertext should come up with gibberish, junk, should not be corresponding to some meaningful encryption of some meaningful messages. So this kind of pattern is not good at all. In reality, we use a version of RSA that has a padding, has special structure, has random information in it that just disrupt this type of predictability in the deterministic determinism in the encryption. So in reality, you'll see that it's a lot more complicated. A family of RSA standards is referred to public key cryptography standards. There's just lengthy specifications. You can read it if you're interested. A lot more complicated than the actual implementation. So that is RSA encryption scheme. We also want to say a little bit about RSA signature scheme. Of course, the signature scheme in general doesn't have to be RSA. As long as it preserves message integrity, then it's a good signature scheme. Encryption is for confidentiality, signature is for integrity, making sure nothing gets tampered with, and so on. On the current internet, the de facto standard is RSA, digital signature scheme, even though NIST has what is called a digital signature algorithm as a standard based on discrete log assumption. RSA, again, factorization assumption. So let's, in digital signature scheme, doesn't have to be RSA again, is for making sure the message is not tampered with, and also authenticating the origin, in proving to people that this is indeed signed by Alice, signed by Bob, signed by the bank, and etc. People cannot forge the signature unless they steal the key. 3 operations: key setup, sign, and verify. So without telling you how this is implemented, I can just describe on a very high level that RSA, digital signature scheme, the key generation is the same. And then you will have 2 keys, one private, one public. The private is for signing, and you don't reveal it. The public key, you reveal it, you distribute it as broadly as possible, so people can use the public key to verify the signatures signed by you. And at signing time, the signer will use the private key D to create a signature on a certain statement. The statement, together with the signature and the signer's public key, is sent over to the receiver, and the receiver will be able to verify the correctness of the signature, therefore infer the statement, the integrity, infer the statement's integrity. And it's very important to use the right public keys. If you use the wrong public key, then you may use the hacker's public key. Anyone can generate your own key pairs. I strongly encourage you to try this at home. OpenSSH has free tools to generate free keys, and you may have to move your mouse a little bit so it generates some random bits, have some entropy, so that the keys are different. So I want to say a little bit about the signing. Let's see. Switch back to the tablet. So the setup, the key setup is the same. So you pick PQ, right? P and Q, and then you compute n equals P and Q, and then you also compute P minus 1, Q minus 1, the torsion. And then, you know, say you choose E. E has to be smaller than N, and E and N are relatively prime. E and Z are relative prime. And so then you pick then you compute. Oh, yes. Then you compute D ED mod the torsion function plus 1, that is ED mod. Right, so EN are public key, D are private key, And similarly, you erase Q and P. And then instead of encryption, there's an operation called sign. Sign will take as input a message, D and N. What you do is that you raise the, in order to create a digital signature, you raise the message to a power of D and mod N. This will give you the signature. And then you output the message, the signature, and N and E. You release this. This gets released together so that people can verify the signature. Okay. And then for verify, this is everyone can verify a digital signature. And then digital signature doesn't have to be stored in secret. You can review it. You can share it widely, put it up online, right? And when we look at the public key certificate, it has digital signatures from the certificate authority. You take the message and you want to make sure that is this message being modified, and then you look at the input, part of the input, the public key and signature. And what you do is that you raise the signature to the power of E. Okay, so it's sort of like a reverse encryption, right? So when you sign, you actually decrypt. When you verify, you encrypt. And that's the operation. And then you do modulo N, and then you should get back M, the original message. Suppose you get M prime. Okay, let's call it M prime. And what you do is that you see, is M prime equal to M? And then if yes, and this pass, that means the signature is valid. The statement is valid. If no, then you reject the message. You say, oh, this is not the message is intended to be. For example, you download it to some program, it has a digital signature, and then don't download if signature does not match the original message. And then you can, of course, verify that this you do get your it should work, the correctness, because if its message is not tampered with, what you get is this should be equal to M. And so let's plug in what sig is. Sig, here we said sig is equal to M raised to the power of D. Right, so this is you just according to definition of sig, this is what you have. And then you get into the MDE-ED situation as before, right? And before that, we said that the ED has this special property. It's based on the how it's picked and based on the fact that it congruence to the torsion function. And so this goes back to N. So it works. It's the correctness checked out. All right. So then we go back to, and so it's very important that you do find a piece of paper and have a desk, and then just to write it down and just to double check yourself. And that's also help you to get some intuition of how this works. And so as you can see, only Alice can sign because she has the private key corresponding to the public key. And so only Amazon can sign certain statements and so on. We just showed this, and I want you to go back home and be able to show this yourself, okay? Here, another diagram that shows this. And at the bottom, we said that unfortunately, this naive signature scheme also has a problem, okay? Let's try to understand, but you should, because of the multiplicative property that we've shown, the signature should not, the signature again, similarly to the encryption, should be as random looking as possible, has no correlation, no connection, no relationship to the original message. If the original message has, you know, certain multiplication property, the signature still should look random. Similar to the issues that we mentioned for the RSA naive encryption scheme. So let's, on a very high level, if you may have a situation where a signer generates a whole bunch of signature on a whole bunch of messages, different messages, and the attacker accidentally or intentionally find out certain messages, in certain messages signatures, when you combine them somehow, when you multiply them together, it becomes a signature of a new message that signer has never signed. And so then you can forge signatures. That's bad. So that's exactly the problem. Let's try to understand. Suppose, and we have some numbers. Suppose you have, you know, this type of setup, and then Alice, for whatever reason, has signed the 26 contract. Bob will make her sign all these, you know, contracts because at some point Bob can multiply two contracts, namely one number 5 and one number 17, okay? And suppose that's a contract number or whatever magic number that Alice has to sign. And if you multiply them and the modulo 77, you get back 8. And so that means that you can actually multiply the signatures as shown in the last line, S1 and S2 signatures to those two contracts actually produce a signature of contract 8, which Alice didn't sign to begin with, okay? So that's forging, and so the forged signature is not good, and because we said we want to have non-repudiation, that means some deniability. You want to say, oh no, this is not something I signed. One way to fix this problem, the naive RSA signature schemes problem, is to sign on the hash of the message instead of message itself. Signing on the hash will be able to disrupt the correlation between the original message and the signature. If you multiply, the hash value still has this multiplicative property, but then the original message, the pre-image of the hash does not, because the hash, there's a one level of randomness introduced by hashing. So think a little bit, think about how would you explain that this hash, by having hash, you would prevent the previous attack that we just showed, this signature collision problem. I want to explain quickly what the cryptographic hash is. The typical hash that you learn from the data structure course is not cryptographic hash. Hashing in general means you have something, you know, a bigger input, and then you hash to a smaller input like a digest. But cryptographic hash also has two important properties. One is one-wayness. Of course, it's easy to compute a lot, you know, almost all the hash functions. But crypto hash also prevent you from going back to the original input. If you know the hash value, you still don't know the original message. Collision resistance, and this means it's very hard to find two inputs that produce the same hash value. And of course, this is the ideal property of a cryptographic hash function. The actual implementation may or may not have this property. A stronger form of collision resistance is that attacker can cannot pick a message that will collide to a specific target. And so, so for example, you say, okay, you may be able to find two inputs that collide to the same hash value, but then you may not. If I say, can you find a message that's collide to my social security number? Like I tell you my social security number 1 2 3 4 5 6. Can you find another social security number that produces the same hash value? That will be a lot harder to do from an attacker's point of view. Okay, from an attacker's point of view, it's a lot harder to do. Okay, so sign think a little bit more about how you explain the hash collision prevents the signature from colliding. Okay, it's the signature from colliding. Think how you can explain this. And today I just want to stop here because there's a lot of math and to digest. Read a little bit about, we have the recommended textbook and also a lot of online materials. Have materials on the description of the public key, the DiffieHellman Key Exchange, the cryptographic hash. So we want to come back next class to say a little bit more about the collision issues and what happened there. And I also want to start to have the written homework. I'll mention it a little bit. We give out an assignment later. And in the meantime, if you're looking for a project partner, please let me know. All right, that's it. Thank you so much. Bye.